One frozen scar sits at the very bottom of the moon. It spans nearly 13 miles across the lunar surface. Inside its rim, the rocky floor drops miles down into total permanent darkness. This is Shackleton crater, and this single hole in the ground is about to dictate the next 50 years of human space travel. At current rates, space programs are burning millions of dollars just to fight Earth's gravity. Every pound of gear needs fuel to lift it. That fuel adds weight. That weight requires even more fuel. It is a brutal cycle that has killed ambitious space programs for decades. But Shackleton crater offers a way out. It holds the two exact things you need to build a lasting presence in deep space: power and water. That combination changes the math entirely. It shifts the whole dynamic, much like how a solid business analysis completely rewrites a startup's pitch to venture capitalists. Once you prove the resources are there, the funding and the scaling make sense. NASA and China know this. Both are aiming their next major missions right at this specific target. The rim of Shackleton stays bathed in sunlight for almost 90% of the year. Solar panels need light to make electricity. Most places on the moon go totally dark for 14 straight days. Equipment freezes, batteries die, but Shackleton's rim barely sees the dark. That means you can run power systems almost non-stop. You get steady, reliable energy. Down below, the crater floor never sees the sun at all. Temperatures down there plunge below -280 degrees Fahrenheit. That kind of extreme cold creates a trap. It catches water and freezes it solid for billions of years. Think about that for a second. You have near constant power up high and ancient ice trapped down low. It is the perfect setup. But knowing the ice is there and actually using it are two very different things. For a long time, engineers could not prove what was hiding in the dark. Early cameras looked down into the crater and saw nothing but black shadows and gray dust. Some scientists thought the ice theory was a bust. Then the tools got better. NASA sent the Lunar Reconnaissance Orbiter, or LRO, to map the moon. It carried a radar system called Mini-RF. Radar does not need sunlight. It shoots radio waves down into the dark and listens to what bounces back. Dry dust bounces the signal one way. Frozen water mixed into that dust bounces it another way. The radar picked up bright echoes from the shadows. It was not a solid sheet of pure ice. It was messy. The data showed ice grains mixed right into the dirt, maybe making up 5 to 10% of the ground by weight. That might not sound like a lot, but when you have a crater the size of a small county, 5% adds up to millions of tons of water. Here is how they actually did it. They did not look for a shiny skating rink. They looked for the specific way radio waves twist when they hit frozen material. Physics behaves predictably, and the radar proved the ice was real. Now the challenge shifts from finding it to pulling it out of the dirt. The technical method is simple but hard to build. You cannot just drill a hole and pump water out. The soil is rock hard. Instead, autonomous robots will scoop up the icy dirt and drop it into a heated oven. They use the solar power from the rim to heat that dirt to about 300 degrees Celsius. The heat forces the water to turn into vapor. Pipes catch that vapor and cool it down until it turns back into liquid water. Once you have liquid water, you hit it with electricity. This breaks the water apart into hydrogen and oxygen. Those two gases are the exact ingredients you need to make high-performance rocket fuel. That is the real breakthrough. You are not just making drinking water, you are building a gas station in deep space. If a rocket can launch from Earth, fly to the moon, and refill its tanks in orbit, everything changes. You do not have to carry all your fuel with you from the start. Taking fuel out of the equation means you can launch smaller, cheaper rockets, or you can fill big rockets with heavy cargo instead of heavy fuel. Making fuel on the moon takes roughly 6 times less energy than dragging it up from Earth. At over $1,000 to launch a single pound into space, that local fuel cuts the price tag by millions. It changes space travel from a series of expensive stunts into a working transportation network. This is where the competitive race gets intense. The United States and China are both reading the same physics, both know the math, and both are targeting the exact same ridges near Shackleton crater. NASA has the Artemis program. Artemis wants to put humans back on the surface later this decade. They are using the massive Space Launch System rocket and the Orion capsule. They also hired SpaceX to build the landing ship. China has the Chang'e program. They are playing a very fast, very steady robotic game. China plans to send Chang'e 7 to the South Pole around 2026. That mission will drop a lander, a rover, and a jumping robot called a hopper right near Shackleton. That hopper is a brilliant piece of engineering. Wheels get stuck in the fine, powdery moon dust. The hopper ignores the dust. It just jumps in short, controlled arcs. It will jump down into the dark craters, scan the ice directly, and then jump back out into the sun to recharge. Nobody has tried this before. If China maps the best ice pockets first, they gain a massive strategic edge. Information is leverage. Space agencies are reading the terrain and positioning themselves carefully, almost like a netter in volleyball reading the opponent's offense to set up the perfect block. You have to anticipate the move before the ball even crosses the net. NASA is taking a different path. They are focused heavily on keeping human crews alive. Artemis II will fly astronauts around the moon in 2026 to test the heat shields and life support. Artemis III will follow with a real landing attempt a couple of years later. Human missions move slower because the safety rules are incredibly strict. One mistake kills a crew. NASA prioritizes testing over speed. But the scoreboard shows a clear timeline gap. China plans to land robots in 2026. NASA plans to land humans later. The side that gets the best maps first gets to pick the best parking spots. But nobody can actually own the spot. The Outer Space Treaty of 1967 bans any country from claiming territory in space. You cannot plant a flag and build a fence. You cannot declare Shackleton Crater as American or Chinese land. Both nations sign that treaty and both follow it. However, the treaty has a rule called due regard. It means you cannot interfere with someone else's mission. You cannot land your ship right on top of their ship. This is the part most people miss. The conflict on the moon is not about borders, it is about dust. When a massive rocket engine fires near the ground, it blasts lunar dirt outward at high speeds. The moon has no air to slow that dirt down. It acts like a sandblaster. During an Apollo mission, dust from a landing hit a robotic probe sitting a whole football field away. The new landing ships, like the SpaceX Starship, are 50 meters tall. That is as tall as a 15-story building. When a ship that big lands, the dust cloud will be huge. If China sets up solar panels on the best ridge, NASA cannot legally land a massive ship right next to them. The dust would ruin the Chinese equipment. It would violate the treaty. The exact same rule applies to China landing near American gear. Because of this physics problem, whoever lands their hardware first creates an automatic safety bubble around it. Not a legal border, a physical hazard zone. Since there are only a few perfect ridges that get constant sunlight, those spots will fill up fast. And this is where it gets interesting. The high ground on the rim is not just for solar panels, it is also the perfect spot for communication towers. A tall antenna on Shackleton's rim can talk to Earth and talk to ships in lunar orbit at the same time. It acts as a giant relay hub. If you control the communication hub and the fuel supply, you control the logistics of deep space. You do not need a military base, you just need the infrastructure. Once the infrastructure is running, everyone else has to work around your schedule. SpaceX is helping drive this reality. They prove that reusable rockets change the market. By landing their boosters hundreds of times, they force launch costs down. Now they are building Starship to carry massive loads to the moon. China's flying frequently too. They launched 67 times in 1 year. The United States launched over 110 times that same year. The hardware is getting cheaper, the computers are getting smarter. Modern landers use onboard cameras to compare the ground to digital maps in real time. They can steer themselves away from boulders in a split second. This terrain relative navigation takes the guesswork out of landing in the dark. Let that sink in. We are no longer guessing where the ice is. We are no longer guessing how to land there. The physics wall has not moved, but the engineers have built a ladder right over it. Early tests might only produce a few drops of water. But once they prove the ovens work without jamming from the dust, the system will scale. It is exactly like the early oil fields. You start small to prove the flow. Then you bring in the heavy machinery. A cluster of 10 robotic processing rigs could eventually spit out tens of tons of rocket fuel every single year. That fuel will sit in tanks orbiting the moon. When a ship heads to Mars, it will launch empty from Earth. It will save millions of dollars by leaving its heavy fuel behind. It will cruise to the moon, fill up at the orbital depot, and fire its engines for deep space. Shackleton crater is the key to that entire chain. It is the power plant, the water well, and the cell tower all rolled into one. Engineers have chased this dream for a long time. Back in the 1990s, they ran into serious limits. The solar panels back then were too weak to provide the intense heat needed to bake the lunar soil. The robotics were clumsy and lacked the fine motor control to operate in total vacuum. One team at NASA tried to run a vacuum test on an early mining prototype. It failed in just 30 seconds. The microscopic glass-like dust instantly clogged their filters. The entire system shut down hard. In another cryogenic trial, a prototype drill seized up completely. The extreme cold locked the metal bearings solid. They had to invent a completely new type of low-temperature grease just to keep the drill turning. Small fixes like that prevent massive mission failures. Those early failures proved how brutal the lunar environment really is. Temperatures near the rim swing wildly. An instrument can go from baking in the sun to freezing in the shadow in a matter of meters. The swing is over 500 degrees Fahrenheit. If you design a robot to survive the heat, the cold breaks it. If you design it for the cold, the heat melts it. Shackleton crater solves part of this problem by offering stable zones. You put your sensitive power gear up in the permanent sunlight. You send the rugged mining tools down into the permanent shadow. You separate the problems. This is why the mapping phase took 15 years. NASA's Lunar Reconnaissance Orbiter has been circling the moon since 2009. It used a laser altimeter to map the jagged walls of the crater with meter-level precision. The data it sent back was not pretty. Some of the slopes tilt more than 15 degrees. If a lander touches down on a 15-degree slope, it tips over. The mission ends before it even begins. Engineers had to find flat pockets under 7 degrees of tilt. During early planning, many proposed landing spots failed the slope checks. Some were just 1 or 2 degrees too steep. The teams had to redraw the safe zones over and over again. The final maps revealed safe landing pockets that are sometimes only a few hundred meters wide. You have to hit a tiny target in the dark, from orbit, while moving at thousands of miles an hour. China faced the exact same brutal math. Their Chang'e mission planners mapped the shadow movements across the pole. They identified specific ridge points that stay bathed in sunlight. Independent teams from rival nations looked at the data and reached the exact same conclusion. Shackleton is the prize. But what happens if the ice is not there? What if the radar signals were just a glitch? There was a moment when one radar pass showed weaker returns than expected. Analysts panicked that the ice signal was just background noise. They rechecked the calibration carefully. The follow-up scan confirmed the signal was totally real. It was not noise, it was just patchy. The ice does not sit in a uniform layer. Some spots are rich, while others are bone dry. This patchiness means mining operations have to be smart. You cannot just scoop blindly. The robots must sniff out the highest concentrations of hydrogen before they dig. Even if the worst-case models are true and the ice concentration drops below 1%, the missions still work. A single robotic digger processing tons of soil can still yield hundreds of pounds of water. The extraction just takes longer. That kind of built-in resilience gives planners the confidence to bet billions of dollars partners on this strategy. It is not a gamble. It is a verified supply chain waiting to be activated, and the timeline is accelerating. We are no longer waiting for the distant future. By late 2026, the hardware hits the dirt. China's Chang'e 7 will test the hopping probe. If that hopper jumps into the dark and finds pure ice crystals, the rush will begin. NASA's Artemis flyby happens around the same time. Then the heavy cargo ships arrive. The United States brings decades of unmatched experience in keeping humans alive in deep space. China brings a flawless recent record of automated lunar landings. Both are expanding their cargo capacity rapidly. The scoreboard proves the capability gap. China successfully returned lunar samples in 2020 with Chang'e 5. They followed it up with even more complex operations. NASA has not brought back a moon rock since 1972, but NASA's commercial partners are building the most powerful rockets ever flown. The Falcon 9 booster has landed over 200 times. No other rocket has proven that kind of reliable reuse. The gap between the leaders and the rest of the world is massive. Pulling water from a desalination plant on Earth costs about 50 cents to $2 per ton. Lifting that exact same ton of water into lunar orbit can cost over $1.5 million. That price tag destroys mission budgets. But if you build the fuel plant at Shackleton, the cost of lunar fuel could eventually drop below $1 per kilogram. That is the lever that moves the world. It flips the profit margins for private companies. It allows government agencies to stretch their budgets infinitely further. And it creates a secondary market. Once the fuel flows, commercial groups will want to export it. Oxygen is in high demand for life support. Hydrogen is the ultimate propellant. A cluster of companies could set up shop along the sunlit ridges, processing dirt and selling the gas to passing ships. But this requires coordination. If a private company lands a supply ship too close to a government science station, the dust plume could ruin millions of dollars of sensors. The United Nations requires countries to report their missions to prevent this. 3 past examples show the trend. Apollo missions publish coordinates early. Soviet Luna missions did the same. Modern Artemis and Chang'e filings follow that exact pattern. If a nation ignores these rules and damages another country's hardware, the diplomatic backlash would be severe. Nobody operates in total isolation. Space missions rely on global tracking networks and deep space communication arrays. You break the rules, you lose access to the network. That acts as a built-in brake against reckless behavior. NASA reinforces this with the Artemis Accords, a set of voluntary safety guidelines. China has its own framework called the International Lunar Research Station. They are separate agreements, but they aim at the exact same goal: sustained, safe operations on the lunar surface. This is the long game. The competition is fierce, but it is channeled into engineering excellence rather than territorial disputes. You win by building a thermal oven that does not jam. You win by writing landing software that recognizes dangerous shadows in a fraction of a second. You win by proving your solar panels can survive the massive temperature swings of the lunar dawn. The strategic reality is set. Shackleton Crater controls the power, the water, and the logistics for deep space. As launch cadences increase, the gap between those who can build lunar infrastructure and those who cannot will become permanent. The next 2 years of robotic and crewed flights will lock in these early advantages. Whoever successfully turns that frozen dirt into rocket fuel first will dictate the future of the solar system.